process on our lecture series of calculus, and it's been a wonderful moment. I'm just so happy we've moved to the last unit on calculus, which has to do with integration, or as others call it, differentiation or anti-differentiation. Any of it goes. So what is the focus under integration? We are going to look at certain rules of the game and apply it on certain functions. So I want to change my pen to blue. We'll look at rules of the game and apply it on certain functions, just as we did in differentiations. Okay, so first, what is the intuition? As I always want my students to have an intuition or a fair deal of what we are into. So mostly integration can be of a concept of finding an area under a curve. This area under the curve can either be on a closed interval or not, as you can see in slide 2. I don't think this is just of functions, but it can be applied. It has very important applications. Okay, and we'll go through that. You know me very well. Having gotten the intuition for finding area under a curve, we have a notation. The notation is mostly an elongated s with whatever we have here as the integrand. So the function under the integral sign is called an integrand, and what we have here is mostly the variable of interest. So we call it the variable of integration, or integrating with respect to this variable. Just as we had differentiating with respect to such a variable, no? So I'll have it this way: dx. So the variable of differentiation is x, and integration, the variable can be anything as well. Okay, so that is it. We can also see that we said derivatives are integrations or anti-differentiation has a relation to do with our differentiation. It's just differentiation in reverse. So if I find a small change, it's the same as the x dy, it is related in a form of integrating the function with respect to the x. That is the reverse operation. So I have an interesting image for you to just have a feel of it. It says, which of these came first? Is it the cock, or can I say the hen, or the egg? Which of them came first? Is it the derivative or the integral? It means a hen, or I'm not so sure that it's a hen or a cock. It gives birth or lays an egg. And if I integrate the egg, I'm going to get back whatever species I have. So which of them came first? There's a question for the ghost for you to answer. And so that is the interesting relation between integration and differentiation. Whenever you differentiate, the resulting value, when you integrate, you must get back your derivative value. Now let's move to one interesting concept, which is the fundamental theorem of calculus. It has to do with differentiations and integration. As we said, integration is an area under a curve. So if you look at the two curves given, if I differentiate a function of this nature, I could get a resulting value. I'm using f of x. So note the difference. There's capital F, that's the derivative function, and when I integrate, I get small f. Note the difference. Plus some constant. Okay. If I do a cross multiplication, it means I'm going to have the x here. The x here travels to this part of the equation, and I have d. Then I integrate both sides of the integration. So I still have integral small f of x dx. Okay. Now there's this relationship. The integration and derivative are inversely related. It's just like in calculus we had the exponential and then the natural log. They are related, and so they cancel out. So it means I'll end up having f of x plus the c equal to integral function here. What can I do now? So you realize that this is equal to that, but if the area under the curve has a closed interval of the same function, then means what I'm going to do is I'll evaluate this f of x at b and then a, which is the difference between b and then the difference between a without the c. The concept of integration vanishes because now we are certain it is finite. So it means that you can have finite integral or definite integral, let me put that way, and indefinite integral. So this part is the indefinite integral because there's no limit of integration given. And this is definite, it is certain because there's a limit of integration given. And that is a fundamental theorem of calculus between differentiation and integration. All that I have done here can be seen in slide 4. Now take note, the difference is not the lower minus the upper. It is not this. It would always be this. It can only be this from if the integral is has a lower of b and upper of a. So it's always the upper minus the lower. Okay, that is it. And so let's quickly move to common functions, and let's apply the rules first. So I want to scroll to the last bit of this slide for you. That is slide 5. I have certain rules of the game to obey. Funny enough, I have the derivative aspect of it, and I want to look at the integral aspect of it. So for a constant, I'm taking the constant first. The derivative of a constant we know is 0, but when we integrate a constant, it is not 0. It becomes a constant times the variable of integration plus a constant of integration, c. So a is not the same as c. A is a constant on its own, but c is a value of interest. It is called the integration constant or constant of integration. Okay. Now let's take the multiplication of a constant by a function. We know there's derivative form. And what do we get for the integral form? I have my constant, and then I can now integrate the function. Here we are using x. Okay. Now the power rule. We know the derivative of the power rule is in this form, but how do I integrate such a form? For this aspect, it is we add 1 to the numerator and divide it by that same rule. So add 1 and divide by it. Unlike the derivative, we multiply and we subtract. Now the sum and difference rule. If I have derivative, I can simply sum their derivatives. It's the same property for integral. So I can find the integral of each of them and then sum or take the difference of it. That is what this rule will help you to do. Now with the exponential part, we already know this guy. What happens for the integral? Instead of multiplying, it's going to divide. So you take note of the differences here. Instead of multiplying, we divide. Forgive me here, I have to now add a constant of integration because I've done the simplification. So the same thing applies here. I have to add a c. Okay. But here I can't add c because I have not evaluated the integral. So I just leave it like that. Now let's take another exponential form here. ax. We went through all this in the differentiation aspect and we obtained this by in integral. It rather divides. And then we add a constant of integration c. Now the natural log, if I differentiate, I get this. But when I integrate, now when I integrate 1 over x, I should get back my ln of x plus the c. So if I integrate this guy, I should get back the ln. But if I differentiate this, I should get that. So the same thing, if I integrate this part, I should get this guy. And then you can now get it done. And then the last things are the tricks. We went through the derivatives of tricks, and here if I should integrate cos, I should divide the constant by it. Sin ax plus c. Now note what happened. We don't have a negative sign here, so we become positive instead. But if I have a sign, then rather now becomes the negative of it. Cos ax plus the c. For tan, you can verify it by using the sine and cos identity. Now you realize that these are not magic. They are not magic. When we wanted to prove these functions, we had to go through the first principle using this limit property. In the same way, we can prove for these identities we've obtained. And in my next videos, or in the course of the session, we'll go through these proofs together. But for now, let's take the identities here. They are very simple to do. Let's take examples for this first session and then we'll end it. So examples, I'm going to take common functions. That has to do with slide 6, 7. Alright, so let's look at the first function. As a constant, I'm integrating a constant with a variable t. We're not integrating a constant as 0. No, differentiating a constant is 0. By integrating a constant, is that constant by the variable of interest plus integration constant c. The second example is not going to be 6x as I would expect, that is derivative. It's rather going to be division because it's an integration part. That is going to be, if it was differentiation as I said, it was going to be 6x. But this is not differentiation, this is integration. And so I have 3x2 plus 1 over 2 plus 1. And that's going to be 3x cubed over 3, which is equal to x cubed plus c. But because it's definite integral, I have to evaluate this s cubed at the value is given as, let me write it well, s cubed, as s cubed at 0 to 2, which means 2 to the power 3 minus 0 to the power 3, which is simply going to be 8. Okay, because a definite integral. So that is it for this part. Now if I move to the exponential rule, what I'm going to do is to differentiate what I have here. If I differentiate, I'm going to get 2. Okay, so I see you have 2a, differentiate with respect to a, and that is going to be 2. So if you differentiate, what you do now is to divide that derivative function and then add your integration function plus c. If it was derivative, we would have differentiated and get 2 and just multiply by it. So note the difference between differentiation and then integration. Okay, now let's take the next example, which is sum and difference rule. What I can do here is to take a term by term, integrate this guy plus integrate this term plus integrate the last term. That is the sum and difference rule. So this is going to be equal to, by the power rule, I'm going to get 3 on 6x to the power 6, you believe that? Plus, if I integrate this part, I'm going to get 7 on 3x to the power 3, and if I integrate this part, it is just 0. Oh, I keep mixing differentiation by integration, that is 8x plus c, because it's an indefinite integral, and that is just that. You can simplify further if you have to, because over here I'm going to get 1 on 2. Okay, so the last one to the same thing, I can integrate 4 on m, the m separately, plus integrate 3m on m, plus integrate 2m to the power 4 on m, the m. That's still the sum and difference rule. If I integrate this, I have 4 integral 1 over m, the m, plus I have 3 on 3 cancels, I have integral of m, the m, plus 2 comes out, and I have integral of m cubed, the m. I've simplified this further, so I get 4. If I integrate this part, it is the ln of m, plus integrating this by the power, I have 1 over 2 m squared, because I add 1 to the index. This is as if I have m to the power 1, and so I have m 1 plus 1, m1 plus 1 all over the 1 plus 1, which is m squared over 2, and that is what I have here, plus 2 over 4 m to the power 4. For the power rule for both integration differentiation, they are not just difficult, they are something simple. You can simplify further if you can, and this how the examples is being done, plus a constant of integration. Alright, so in the next, I'll end here. In the next episode, we are going to take more of word problems on integration of simple functions, okay, through with this fields. And so take your time and then take more examples by simply applying the rules. And that is it for today. Thank you.